that is, it allows us to describe particles as waves. But how exactly do we describe our waves?
Okay, units.
Intensity or brightness of that electromagnetic wave. So basically, for electromagnetic waves, as the one shown below, we were able to relate the frequency of the wave to the energy of the photon, and we were also able to relate the amplitude of the wave to the measure of the strength of the electric or magnetic field, or to the intensity or brightness of our wave. So basically, if we have the following oscillating electric and magnetic field, so basically this is our electromagnetic wave that consists of oscillating electric fields and oscillating magnetic fields. The amplitude represents our strength of electric field. So because the intensity of an electromagnetic wave is directly proportional to the square of the amplitude, and the amplitude is the electric field, so that means our intensity is directly proportional to the square of our strength of the electric field. Now, what this basically means is the following. This means that in order to actually describe material particles such as electrons as waves, we must be able to use these same physical quantities such as frequency, wavelength, and amplitude. Now, Bernoulli was able to basically relate the momentum of a particle such as an electron to the wavelength or frequency that that particular particle produces, and the equation is given by this formula. So if we take h, Planck's constant, and divide that by the momentum of that particle such as an electron, that gives us the wavelength that is produced by that particle, the wave that is produced by that particle. Now, because the wavelength is equal to c, the speed of light in a vacuum, divided by the frequency of oscillation of the wave, we can take this equation and we write it in terms of our f, c, h, and p. So basically, we build a relationship between the frequency of the particle wave, the wave produced by the particle, and the particle's momentum. So this is analogous to basically relating the energy of a photon to the frequency or wavelength of that electromagnetic wave. Now, the question still remains. We were able to build a relationship between momentum and frequency or wavelength, but what exactly describes the amplitude or displacement of a particle wave? So we saw in the case of electromagnetic waves, the displacement describes the electric and magnetic fields, but in quantum mechanics, it is a quantity known as the wave function that basically describes the amplitude or displacement of our particle wave, and this is given by the Greek letter psi. So, this wave function given by psi basically describes the height of our displacement, which in turn describes the strength of the field that is produced by that particle wave, and this field is commonly known as matter field. So, psi, our wave function, is basically a function of two variables, as we'll see in a future lecture. It's a function of the position as well as of time. Now, we basically define matter wave to represent the wave that is produced by a particle. So, instead of calling it a particle wave, from now on, we're going to call it a matter wave, and a matter wave consists of matter fields. So, once again, the wave produced by particles, such as electrons, is commonly known as matter waves, and our wave function basically describes the strength of the matter fields of these matter waves. Now, how exactly does one go about interpreting and understanding what exactly a matter wave is? So, let's begin by recalling electromagnetic waves once again. So, if we're taking the point of view of a wave, then we know for the electromagnetic wave, our intensity of the wave is directly proportional to the square of the strength of our electric field. On the other hand, what if we take the point of view of a photon, of a particle? So, if we take the view of a particle, the intensity of the electromagnetic wave is directly proportional to the number of photons that are incident to some surface area. So basically, the intensity of our electromagnetic wave, if we're looking at it from the point of view of photons, is directly proportional to the number of particles that are incident, the number of photons. And because I is proportional to E squared, these two equations combined form equation 1. So N, the number of incident photons, is directly proportional to the square of the electric field. So basically, the greater the number of photons that are striking some surface area, the stronger the beam of light and the brighter that beam of light is. Now, what if we take a single photon? How exactly can we understand this equation for a single photon? So if we take a single photon, this equation can be interpreted in a slightly different way. For a single photon, this E squared term is basically a measure of the probability of a photon being found in that particular position. So, the greater the E squared term is, the greater the probability is that our single photon is found in that particular location. And the smaller the E squared term is, the less likely our photon is found in that particular position. So, in a very analogous way, matter waves can be interpreted in a similar way as described in this section. So basically, if we take equation 1, what equation 1 tells us about matter waves is the number of particles found in a matter wave determines the strength of the matter field. So basically, the wave function, which basically tells us the strength of that matter field, also tells us how many particles we have inside that matter wave. So once again, what the wave function actually tells us is the displacement of our matter wave. It tells us the strength of our matter field in the same way that our displacement for electromagnetic waves tells us the strength of our electric field for electromagnetic waves. Now, if we take the wave function and we square that wave function, we get something known as the probability density. So if we're looking at a single particle, such as an electron, then the probability density for that single particle at any given point in space and time tells us the probability of finding an electron at that particular moment in time and point in space. So if that probability density is high, then there's a high probability of finding our electron in that particular region in space and point in time. So once again, the wave function of our particle basically tells us the magnitude of displacement or the magnitude of the matter field of our matter wave produced by that particle. And if we square that wave function, that gives us the probability density, which basically gives us a mathematical probability of finding an electron in a certain given region and certain point in time. since electrons not only act as particles, but they can also act as waves, we might expect a diffraction pattern to be formed when electrons are about to flow through double-slit screen, as long as the size of the openings of the slits is on the order of the wavelength of the wave produced by those electrons. So, to see exactly what we mean, let's conduct the following thought experiment. Let's suppose we have a double-slit screen with the size of each one of these openings is on the order of the wavelength of the wave produced by those electrons. So we allow those electrons to basically flow throughout two openings, and eventually they form a diffraction pattern on the following viewing screen. So constructive interference of the waves leads to bright fringes, and destructive interference leads to dark fringes. So this graph basically represents the intensity of that fringes formed on the screen by our electrons. Now, these hugs, these clefts, basically represents the regions of our bright fringes, and these drops represent the regions of dark fringes. So as we might expect, the most intense, the brightest fringe is formed at the center, and the intensity decreases as we get farther away from the center of our viewing screen. So as we saw in the double-slit experiment conducted by Young, light forms an interference pattern that can be visualized by the eye. Now, although electrons form a similar pattern, to actually visualize our fringes formed by the electrons, we have to use a fluorescent screen. So that basically means anytime an electron strikes that fluorescent screen, it basically glows. So that location where it strikes glows. So in this particular experiment, we had many electrons passing through our two openings at any given time. But what happens if we decrease the number of electrons that pass through the two openings to the point where only one electron enters any one of the two openings at any given point in time? So basically, one time a refraction pattern could be observed a refraction pattern as well. So initially, the locations of the electrons in the screen will appear to be completely random, as shown in diagram 1. So we have the electrons in our screen, but the locations appear to be completely random. So no diffraction pattern appears initially. However, if we allow the experiment to run within one time, a diffraction pattern will in fact emerge, as shown in diagram 2. So we have the center fringe, the brightest fringe, and we have two more fringes, and these regions in the middle that are gray represent our dark fringes. That's where destructive interference takes place. So basically, although it would be impossible to predict where each individual electron would strike the screen, we could in fact predict the probability of an electron striking a certain region of screen. So once again, even though it's impossible to predict exactly where the electron will strike, and it's impossible to actually follow the pathway of any single individual electron, what is possible is to predict the probability of an electron hitting a certain region. In fact, we see as these fringes are formed, most of the electrons are in fact hitting these regions, and very few electrons are hitting the following dark region. So this probability is given by taking the Rayleigh function and squaring that, and this is known as the probability density.
QR コードを東大線竹橋ステーションに乗っております。国際協力賞、国際協力銀行になったらパーキングがありまして、そこまでで歩行者中になっていまして、ずっと英語な知恵ということになっていますね。工場になっています。セーフティーだそうです。大成建設さんの日清間脱粉なるがありました。さんが
This implies that the electron must travel through both openings at the same time to produce the wave interference, and this only takes place if the electron behaves as a wave when it actually passes through those two slits. So once again, this is exactly what we're talking about. So let's say here is the following. At any given time, a single electron is allowed to pass through any one of those two openings at any given moment in time. So we have one electron passes, then we have a second electron passes, then we have a third electron that passes, and so on. So basically, if the electron acted as a particle, then that means the electron can only pass through either this opening or this opening. It can't actually pass through both openings at the same time. But if it acted as a wave, if the electron behaved as a wave, that implies it could travel through these two openings at the same exact time. And a wave interference pattern, a diffraction pattern, is then formed when our wave travels through these slits at the same time, so that wave interference could actually take place. So what this experiment basically showed is that when the electron flows through our screen, it acts as, it behaves as a wave, so that the electron actually passes through the two openings at the same time, interfering and forming these bright and dark fringes. Now, the second statement that we should basically conclude with is the following. When we treat our electrons as if they were the waves, then this wave function on the side matters for this space and the amplitude of those waves, the amplitude of the beam induced by those matter waves. On the other hand, if we're treating our electrons as if they were particles, then the square of the wave function known as the probability density describes the probability of finding an electron at a certain location at a certain time with some mathematical quantity. As we might already know, quantum mechanics deals with atomic and subatomic worlds. Now, when we make measurements of objects found on the atomic and subatomic level, there always exists an amount of uncertainty that involves those particular measurements. In fact, there is a limit to how precise those measurements can be made, and this is known as the Heisenberg uncertainty principle. Now, as we'll see towards the end of this lecture, the Heisenberg uncertainty principle is a result of the wave-particle duality of matter that exists on the subatomic and atomic level. The Heisenberg uncertainty principle has absolutely nothing to do with the nature of the instrument that we use to measure those measurements. So, to fully understand what the uncertainty principle is, let's conduct the following thought experiment. Suppose we have an electron, and we are asked to determine the position of that electron using some type of hypothetical device. Let's suppose a powerful light microscope. Now, if we want a precise position of that electron at some instant in time, the wavelength of light used by that microscope microscope has to be very small. It has to be on the order of the size of our subatomic particle, our electron. Now recall, if we decrease the wavelength of the light used by the microscope, we increase the energy carried and the momentum carried by the photon of light. So that is given by this equation. The momentum of the photon of light used by the microscope, P, is equal to C, the constant that gives us the speed of light in a vacuum, divided by the wavelength of light used by the microscope, given by lambda. So basically, if we want a more precise location of the electron at some moment in time, we have to decrease the wavelength of light. But if we decrease the wavelength of light, we decrease the denominator and thereby increase P, the momentum of the photon. Now, why is this relevant in our discussion? So let's examine the following diagram. So this is the eye of the observer making our observation. Now, this is the scope of our powerful light microscope. So the microscope uses a certain wavelength of light that is shown by the following orange arrow. Now, in order for us to actually see that electron, our light has to actually interact with that electron. So the photon of light basically collides with the electron, reflects, and eventually reaches the eye of the observer. However, what actually takes place between our electron and photon is a collision takes place. And that collision between the photon and the electron basically transfers some of that energy and momentum to that electron, and the electron moves away with some velocity. So basically, the lower the wavelength is, the higher the momentum of that electron is, and the higher the velocity of that electron is after that collision takes place. So even though we might know the precise position of the electron at that moment in time, because of that collision, our electron will move away with some unknown amount of momentum, with some unknown amount of velocity, and that means we have no way of actually knowing the future position of the electron, and we have no way of knowing the momentum that the electron has if we know the precise position of that electron at that particular instant in time. So, once again, if we want a precise measurement of the electron's position, we need a photon with a small wavelength. However, such a photon will carry a large amount of energy as per this equation, and the collision between the photon and electron will cause that electron to move away with a very high velocity, which will change that electron's position. As a result, although we might know what the position of the electron is at that instant in time, we have no way of knowing the momentum of the electron, and therefore no way of knowing where that electron will be at some future instant in time. So basically, this uncertainty in knowing the position of the electron and at the same time the momentum of that electron, the velocity of that electron at the same time, is the basis of the Heisenberg uncertainty principle. Now, mathematically, the Heisenberg uncertainty principle is given by this equation. Delta x multiplied by delta px is greater than or equal to h bar, where h bar is simply a constant. H bar is equal to h, Planck's constant, divided by 2 pi. So if we divide these numbers, we see that h bar is equal to 1.055 times 10 to negative 34 joules per second. So basically, the delta x is the change in our position of the electron along the x-axis, and delta px is the change in the momentum of our electron, the subatomic particle, along that same x-axis. Now, what exactly is the meaning behind this equation? What does this equation actually tell us? So, this equation tells us that the more precisely we know the position of our electron, the smaller the delta x is, the larger our delta p is, the less precisely we know the momentum of our electron. So basically, if our delta x is smaller, to compensate for that smaller delta x, because this is a constant, the delta p has to increase. So this basically means that it is impossible to measure precisely the position and at the same time the momentum of our particle at some given moment in time. So this does not mean, of course, that we cannot make precise individual measurements. We can, for example, determine the precise position of an object, our electron, at some moment in time, but then the momentum would be completely unknown. So that basically translates into this equation. The smaller our uncertainty is in our position, the smaller our delta x is, the greater our uncertainty is in our momentum, which gives us our future position. So the greater our delta px is. So this basically implies that we have absolutely no way of knowing the future position of our electron if we know exactly where that electron is at that particular moment in time. Now, once again, we have to emphasize the following important point about the Heisenberg uncertainty principle. The Heisenberg uncertainty principle has absolutely nothing to do with the precision of the measuring instrument that we are using. The Heisenberg uncertainty principle is an inherent property of nature and comes from the fact that matter on a subatomic level can act as particles as well as act as waves. That is, the reason an electron does not have a precise location and momentum at any given moment in time is because our electron is not actually a particle. In the previous 7 lectures, we discussed a concept in quantum mechanics known as Heisenberg's uncertainty principle, which basically comes from the dual nature of matter. The fact that matter can act as waves or it can act as particles. So now let's actually apply that principle to solve the following example. So an electron is traveling along the x-axis with a constant velocity of 2 million meters per second. Now, if the velocity of the electron is measured to a precision of 0.15%, we want to calculate the maximum accuracy with which the position of the electron can be measured at the same instant in time. So we're assuming the mass of the electron is equal to 9.11 times 10 to negative 31 kilograms, and our constant h bar is equal to 1.055 times 10 to negative 34 joules multiplied by seconds. So basically, this example is a direct application of Heisenberg's uncertainty principle that relates the uncertainty in position of our electron with the uncertainty in momentum. So basically, it tells us that the uncertainty in our position of the electron along the x-axis multiplied by the uncertainty in the momentum of that electron along the same x-axis is greater than or equal to h bar, our constant. So basically, from the information that we're given, we can calculate what the uncertainty in our momentum of that electron is. What we want to find is the uncertainty in our position of the electron knowing this quantity. So let's take this equation, rearrange it, and solve for delta x. So delta x, the uncertainty in our position of the electron along the x-axis, is greater than or equal to h bar divided by delta px. Now, what exactly is momentum? Well, if we're dealing with non-relativistic momentum, then the momentum p of our electron is equal to the product of the mass multiplied by the velocity. Since we're dealing with the change in momentum p, this is equal to the mass, which is constant, multiplied by the change in velocity of our electron. So let's replace delta px with the mass of the electron multiplied by the change in velocity along the x-axis, also known as the uncertainty of the velocity of our electron. So if we take the uncertainty in velocity of the electron and multiply by the mass of the electron, we get the uncertainty in momentum of that same electron. So let's plug in our h bar, which is equal to 1.055 times 10 to negative 34 joules multiplied by seconds. We divide that by the uncertainty in our momentum. So the mass of that electron, 9.11 times 10 to negative 31 kilograms, multiplied by the uncertainty of the velocity. So 0.0015 multiplied by the velocity of our electron. So this quantity gives us the uncertainty of our velocity of that electron. And this entire denominator, if we multiply this by the mass, that gives us the uncertainty of our momentum of that electron along the x-axis. So from this calculation, we see that delta x is greater than or equal to 3.86 times 10 to the negative 8 meters. So we see that the answer is the maximum precision with which the position of the electron can be measured at the same exact instant of time for this particular velocity. And this particular position of that velocity is equal to 38.6 nanometers. So by the uncertainty principle, the mass simultaneous position will have an uncertainty of 38.6 nanometers along the x-axis. So basically, if we know the uncertainty of the momentum of our particle, which is equal to the product of these three numbers, the uncertainty in the position of that same particle, that same electron along the x-axis is equal to this value. Let us now look at the following example that deals with Heisenberg's uncertainty principle that relates the uncertainty in time and the uncertainty in energy. So, let's begin. An electron in the n equals 2 energy level of the hydrogen atom remains in that level for 80 nanoseconds before transitioning to a lower energy level given by n equals 1. So, in part A, we want to determine the uncertainty in the energy that is released when that electron jumps from n equals 2 to n equals 1. So, let's begin by applying the Heisenberg uncertainty principle that relates the uncertainty in time and the uncertainty in energy. So, the product of these two uncertainties is approximately equal to h bar, our constant. So, 1.055 times 10 to negative 34 joules multiplied by second. So basically, we want to solve for delta E. So delta E is approximately equal to h bar, this value, divided by the uncertainty in time, which is equal to 80 nanoseconds, or 80 times 10 to negative 9 seconds. We divide these two quantities, the seconds will cancel, and we're left with an uncertainty in energy of 1.319 times 10 to negative 27 joules. Now, let's move on to part B. In part B, we want to determine the fraction of energy that this uncertainty represents with respect to the total energy that is released by that electron during that transition. So basically, when that electron jumps from energy level n equals 2 to energy level n equals 1, it releases a photon of energy. So first we want to calculate how much energy is stored within that photon, and then we want to calculate the fraction. So to calculate how much energy is stored within that photon of light that is released during that transition, we have to apply the Rydberg equation, which states that 1 divided by lambda, the wavelength of light released during that transition, is equal to r, the Rydberg constant, multiplied by 1 divided by n1 squared minus 1 divided by n2 squared, where n1 is energy level n equals 1, and n2 is energy level n equals 2, and r is the Rydberg constant. So basically, if we use this equation and solve for lambda, that will give us the wavelength of the photon of light that is released during that transition, and then using that wavelength, we can calculate what the energy is that is stored within that photon, and that gives us the total energy that is released. And then we use that and this result from part A to calculate the fraction of energy that this represents. So let's actually plug in our values. So n1 is equal to 1 and n2 squared is equal to 4. So 1 minus 0.25 gives us 0.75. We multiply that by the Rydberg constant, 1.097 times 10 to the 7 meters to negative 1, and then we solve for our wavelength. And the wavelength is about equal to 1.215 times 10 to negative 7 meters. So now we use the following equation to calculate the energy stored within that photon of light released. So h, Planck's constant, multiplied by c, the speed of that photon in a vacuum, divided by our wavelength, this quantity, and that gives us 1.636 times 10 to the negative 18 joules. This is the quantity of energy that is released when that electron transitions from n equals 2 energy level to n equals 1. Finally, to find the fraction that this energy represents, we take this quantity and divide it by this value. So 1.319 times 10 to the negative 27 joules divided by 1.636 times 10 to the negative 18 joules, and that gives us about 8.06 times 10 to the negative 10, which is approximately equal to a fraction of 1 divided by 1.24 times 10 to the 9. So this is the fraction of energy that this quantity, this uncertainty represents with respect to the total energy that is released during that transition. In the previous lecture, we discussed Heisenberg's uncertainty principle, and we said that the change in position of any object is related to the change in momentum of that same object. So basically, the less we know about the position of the object, the more we know about the momentum of that object, and vice versa. Now, a second useful form of Heisenberg's uncertainty principle involves relating the time and energy of that object. So let's conduct the same exact third experiment that we conducted in the previous lecture. So basically, we want to use a powerful light microscope to determine the position of an electron. So this is our electron. So this is the light wave that our microscope uses. This is the scope of our microscope, and this is the eye of the observer. So basically, to observe that electron, we basically have to collide the wave of light, the photon of light, with this electron. Now, suppose that the photon of light that our microscope uses has a wavelength given by lambda, which is approximately equal to the change in position of that electron during the collision between the photon and the electron. So basically, the photon of light collides with the electron changes in position given by delta x. So delta x represents the uncertainty in our position of the electron, and we're assuming this is approximately equal to lambda, the wavelength of the light used. Now, since the photon travels with the velocity given by c, the speed of light in a vacuum, following the collision of the photon and the electron, it will take the photon a time interval of delta t to travel an uncertainty distance given by delta x. So delta t is equal to the distance traveled by our photon delta x divided by c, the speed of that photon. Now, because we assume this fact, we see that delta x is